In the last lecture, we have discussed in detail the concept of a traveling wave or progressive wave, particularly the plane progressive wave, or you can say the sinusoidal progressive wave. Now, our today's subject is a stationary wave, which is also called a standing wave. So, in this lecture, we will discuss this stationary wave in very detail. First of all, definitely you have a curiosity to know what is this stationary wave and why it is called a stationary wave or a standing wave. In fact, when two waves are superposed, then a stationary wave is formed. But is it possible that any two wave will get superposed and a stationary wave will form? Answer is no. Actually, there is some condition. If you consider that this is your first wave, which I have shown in this figure, and this is moving in positive x direction, okay, and this is your second wave, which is moving in negative x direction. So these two waves are moving in opposite directions, okay. And also consider that if A1 is the amplitude of the first wave and A2 is the amplitude of the second wave, then A1 is equal to A2. Okay, A1 is equal to A2. So we consider two waves moving in opposite directions such that they may superpose and their amplitudes are equal. And apart from that, these waves also move with same speed. But you know, speed v is omega over k. Okay? So definitely, as you have considered that both waves are of equal frequency, it means if you consider that omega 1 is frequency of first wave, omega 2 is the frequency of second wave, then omega 1 should be equal to omega 2. And from here you can see if omega will be same for both, definitely this k will be also same because you consider that v is same. Okay? And if k is same, wavelength will be same. So you can say that when two progressive waves of same frequency and same amplitude traveling in opposite directions get superposed, then the resulting wave created is called a stationary wave or a standing wave. Okay? In fact, this is also possible when you consider that there is a source of disturbance or source of wave which actually continuously emits wave, and here there is a rigid boundary, and from this on this boundary this wave gets incident, and after the interaction with this boundary the wave will get reflected. Now a wave which is moving which is originated from the source, that is incident wave, and another wave which had been reflected, both will get superposed. In this condition too, the standing wave will be formed. But this situation I am not dealing in this problem. Okay? There will be some difference in calculation when you take the formation of a standing wave by an incident wave and a reflected wave. Okay? Here I have actually considered independently two waves which are moving in opposite direction in such a way that they may superpose, and ideally we consider that the amplitudes of both waves are equal, frequencies of both waves are equal, and they are moving in with same speed. Okay? In other words, you can also say that their wavelengths are also equal. Then due to the superposition of such two waves, a new wave will be created or new type of wave will be formed and that very wave is called a stationary wave or a standing wave. Why it is called a stationary wave or a standing wave, we will see later on. In the last of the lecture, we will discuss some important points, and among those important points, one of the points will be to explain why it is called a stationary wave or a standing wave. Okay, there is something which is stationary, and that's why this wave is called a stationary wave. Now, first of all, we are going to find the equation of this stationary wave. By the principle of superposition, you can easily find what will be its equation. For this, let us consider two waves. As you can see, this first wave I have assumed is moving in positive x direction, second is moving in negative x direction. Okay, both are of same amplitude, same frequency, and they are moving with same speed, or you can say same wave number k. Then you know the first progressive wave, both are progressive waves or traveling waves. So the first progressive wave is represented by this equation, as you have learnt in your previous lecture. Psi 1 of xt is given as a times sine omega t minus kx. Okay, this you can see this first equation contains here minus sign, and remember, as I have told you in the previous lecture, that if there is a minus sign before kx or before omega t, then that equation represents the wave traveling in positive x direction. But if both of these terms omega t and kx are positive, then the wave is traveling in negative x direction. So here equation 1a defines the wave traveling in positive x direction, and this equation y2 psi 2 of x and t equal to a sine omega t plus kx, this represents the traveling wave moving in negative x direction. Now, when these two waves will get superposed, then you know what will be the resulting displacement or the resulting wave function. Here psi 1 psi 2 you may treat like displacement, and these displacement actually act here like a wave function. So the resulting wave function or the resulting displacement, if you denote it by the symbol psi, then this psi of xt will be equal to psi 1 plus psi 2 in accordance with the superposition principle, which we have studied in very detail in my previous lecture. Now let us substitute the value of psi 1 and psi 2. You can see this will be a times sine of omega t minus kx plus sine of omega t plus kx. Now you can simplify this result by using the trigonometric formula sine c plus sine d. And you know this sine c plus sine d is what? This is 2 sine c plus d divided by 2 into cos c difference d divided by you can say c minus d or d minus c, because cos minus theta is equal to cos theta. So when you will apply this formula here, at the place of c you can take omega t minus kx, at the place of d you can take omega t plus kx, then you will get that psi is equal to 2a sine omega t plus cosine of kx. It is very easy mathematics. So finally we find that psi of xt is equal to 2a times cosine of kx plus times sine of omega t. Actually this result obtained in this equation 2 is nothing, this is simply the equation of a standing wave. But how you can say that this equation is equation of a wave? In fact, now we will learn some important facts regarding this wave, standing wave. Okay, one by one. In different points, we will learn about the different facts related to this standing wave. So, the first point of discussion, I am actually trying to explain that how you can say that this equation obtained here represents a wave. You know, whenever you have to test that any function psi which is a function of a space and time coordinate, that is x and t, is a valid wave function. It represents a wave only when this function satisfies the classical wave equation. So if that very equation will represent a wave, then psi must satisfy this differential equation, del 2 psi by del t square equal to v square times del 2 psi by del x square. Actually, this is the necessary and sufficient condition for psi to be a wave function and psi representing a wave equation. So let us, you will see, I have actually shown it here by the calculation. But remember that actually this equation 2 satisfies this classical wave equation. And as it satisfies this classical wave equation, so definitely we can say that very equation represents a wave. But as I have told you in my previous lecture, that if a function of x and t is of this form, f of ax plus minus bt, then such a function represents a travelling wave or the progressive wave. You can see the function, the variables x and t are not in this form, that is not in the form of ax plus minus bt, where a and b are constant. So definitely one can say that this equation psi equal to 2a cos kx times sin omega t, this definitely does not represent a travelling wave. It may represent a wave, but it is not a travelling wave. Okay? Actually, what this equation represents, that is called a standing wave. But I have told here that psi defined in this equation 2, whose definition is like this, satisfies this wave equation, classical wave equation. But I have not proved it. So now let us see its proof. This proof is very simple. You can do it, but I have done the algebra. You can see. We will simply find the second order partial derivative of psi with respect to t and x. And then we will check that this equation gets satisfied or not. So let us find del psi by del t. You can see this equation. This will be simply 2a omega cosine of kx times cosine of omega t. But we have to know del 2 psi by del t square. So what will be this? This will be minus 2a omega square cos kx times sin omega t. But you know 2a times cos kx times sin omega t, that is simply equal to psi. So instead of that I have written psi here. So this del 2 psi by del t square is minus omega square times psi. Okay. Now in the similar manner, now let us differentiate this psi with respect to x partially 2 times. And when you will differentiate, then you can see, I am not reading this, you can do it. This del 2 psi by del x square will be equal to minus k square times psi. Okay. Now we have to relate these two partial derivatives. So for that, let us divide this del 2 psi by del t square by del 2 psi by del x square. You can see in RHS psi will cancel, minus sin will also cancel, and we will left omega over k whole square. But you know omega over k is simply v, which is called phase velocity or wave velocity of the wave. So this is v square, and that's why you can say that this del 2 psi by del t square is equal to v square times del 2 psi by del x square. And what is this? You can see this is the classical wave equation. So we have seen that the equation which we have obtained by the principle of superposition, that is psi equal to 2a cos kx times sin omega t, this equation satisfies this classical wave equation, and that's why we can say that definitely this equation represents a wave, and the wave which is represented by this equation, that is actually called a standing wave. Okay, so I think this first point is now very clear to you. Okay, now let us see what is the amplitude of this wave. See this equation, psi equal to 2a cos kx times sine omega t. In fact, this 2a cos kx, this is the amplitude of this wave. If you denote the amplitude of a standing wave by the symbol as, here subscript s has been used for the word stationary or standing. So as is given by 2a times cos kx. Now you can see the amplitude of this standing wave is not constant. Why it is not constant? Due to the presence of this variable x. Since as will vary in accordance with cos kx, and you know cos kx will vary periodically. So you can say that the amplitude of a standing wave is not constant, but it varies with position x periodically, in periodic manner. But this amplitude is independent of time. It will not vary in accordance with time as it varies in case of bits. You have studied the superposition of two simple harmonic oscillations of slightly different frequencies, and the idea of bits actually appear there. And in case of bits, we have seen that the resulting amplitude is a function of time that varies with time. But in this case, in case of a standing wave, you can see that its amplitude is not constant but varies periodically with position, not with time, as happens in case of bits. Okay. Now, how this amplitude will vary, that actually gives two very important concepts. First one is called the concept of node, and another is called the concept of antinode. Node and antinode formation is a basic feature of the standing wave. Such a phenomenon is not observed in case of a standing wave. Okay. In fact, formation of node and formation of antinode is the basic feature of a standing wave. So now let us see what are these nodes, when these are formed, okay, and what are its basic properties. Actually, if you talk about a node or nodal points are those points where the amplitude of the standing wave is minimum. So a node or nodal point is defined as the point for which amplitude as of a standing wave is minimum. Now in the present case, when you take a standing wave which is formed by the superposition of two progressive waves of equal amplitude, although this may be formed by the superposition of two waves of unequal amplitude, that will be not a pure standing wave, that will be partially a partial standing wave. We will talk in the last of the lecture this fact. But here I have considered two progressive waves of equal amplitude get superposed and a standing wave is formed. Actually in this case, the standing wave form is called a pure standing wave. And for a pure standing wave, you can say that nodes are those points where the amplitude of the standing wave is 0. Here minimum means 0. Okay. So for knowing the mathematical condition to obtain the position of nodes, what you will write? You will take as is 0. As is amplitude of a standing wave. But you have seen that as is equal to 2a cos kx. So this 2a cos kx must be equal to 0. But as 2a is not 0, so it means cos kx is equal to 0. And if cos kx is 0, what will be the general value of kx? You know, general value of kx will be equal to 2n minus 1 times pi by 2. Here 2n minus 1 is an odd number. Here n means 1, 2, 3, 4, 5, 6, 7 and so on. Okay. But you know this k, which is called either wave vector or wave number, that is equal to 2 pi over lambda. K equal to 2 pi over lambda. So if you want to express the position of node in terms of the wavelength, then you should write 2 pi by lambda instead of k, and then you can see this pi and this pi will cancel out, and so the position of nth node, which now I have denoted by the symbol xn. I have used the subscript n, which refers that we are talking about the nth node. So xn is equal to 2n minus 1 times lambda over 4. This is the expression by which you can find the position of any node substituting the proper value of n. Okay. So now let us put n equal to 1, 2, 3, 4 and so on for getting the position of first, second, third, fourth and so on nodes. So when you will take n equal to 1, then x1 is lambda by 4. It means first nodal point is situated at a distance lambda by 4 from the origin. Okay. Here this first node is situated. Now the second node x2, this will be n is here 2, so this will be 2n minus 1 will be 3 and this is 3 lambda by 4. Similarly, third node, it is at 5 lambda by 4. Okay. So you can see there are different nodes. This is first node, this is second node, this is your third node and so on. Now let us try to find what is the separation or spacing between two successive or two adjacent or two consecutive nodes. You can see x2 minus x1. This is actually equal to x1. Okay. And this is x2, position of the second node. This is x3, position of the third node. So x2 minus x1 will give separation between first and second node. And you can see the value of x1, x2 here. This will be 3 minus 1 times lambda by 4, which is lambda by 2. So the spacing between first node and second node is lambda by 2. Similarly, the spacing between the, here there will be 2. Second and third node, this will be x3 minus x2 and that will be again lambda by 2, you can see. So if you will find the spacing between any two successive nodes, any two adjacent or consecutive nodes, you will get that this spacing is simply lambda by 2. So you can say that in a stationary wave, nodes are equally spaced, and the spacing between two adjacent nodes is lambda by 2, and the minimum amplitude of this stationary wave is equal to 0. Okay. So in this way we have obtained the position of the different nodes and the spacing between two adjacent nodes. Okay. Now see a very important fact regarding these nodal points. As you have seen, at nodal points AS is 0, amplitude of the standing wave is 0, and you know the equation of a standing wave is given as psi of xt equal to as times sine omega t. We have seen earlier. Here, this psi represents the displacement of the particle at position x at time t. But if you are talking about a standing wave, you know AS is 0 at nodal points. At all nodes, AS remains 0 in spite of time, at any time. So if AS is 0, so definitely this psi, which is displacement of the particle, that will be 0 at all time at nodal points. So what does it mean? It means the particles at the nodes never get displaced. Okay? It means nodes are permanently at rest. Nodes are permanently at rest, it is never in motion, the particles at the nodal point never get displaced. But can you think that the nodes are permanently at rest, but are they clamped rigidly? Answer is no. We have not physically clamped those points with any rigid support. In spite of that, nodal points are never in motion. So this is a very important point, very important property of nodes. Nodes are permanently at rest, but they are not physically clamped. Okay, this is a very remarkable fact. So this was all about the nodal points. Now we will talk about antinodes. This is just the reverse situation of nodes. When you talk about antinodes, actually these are those points where amplitude is maximum. You can see, when you have talked about node, you have told that nodes are those points where amplitude of the standing wave is minimum. But at antinodes, the amplitude of a standing wave is maximum. Okay? So now let us see what will be the maximum amplitude and when it will actually happen. Let us see. As you know, the amplitude of a standing wave is given as as equal to 2a cos kx. Now, since 2a is constant, so definitely this as will vary in accordance with cos kx. So, when cos kx is maximum, then as will be maximum. Okay? And what is the maximum value of cos kx? When you say maximum value of cos kx, it means maximum value of modulus of cos kx. Why modulus? Because we know that amplitude may be positive or may be negative. So for getting its maximum value, you must take modulus of cos kx. But we know that maximum value of mod of cos kx is equal to 1. Or you can say when cos kx is equal to plus minus 1, either plus 1 or minus 1, then mod of cos kx will be 1 and then this amplitude will be maximum. And what will be that maximum value? For that you have to take the maximum value of this cos kx, which is plus minus 1. So you can see that as maximum will be equal to plus minus 2a. Okay? And this is actually the condition when antinode will be formed. So if you want to know the position of antinodes, you must start with this condition. That is, at the position of antinode, cos kx must be equal to plus minus 1. And you know, if cos kx is equal to plus minus 1, what will be the general value of kx? You know, that will be equal to n pi, where n will be 0, 1, 2, 3 and so on. In fact, when you will take n equal to 0, kx will be 0 and cos 0 is 1. And when you will take n equal to 1, then this will be pi and cos pi is equal to minus 1. When you will take n equal to 2, this will be 2 pi. So cos kx will be cos 2 pi, which is plus 1. So alternately, the value of cos will vary from plus 1 to minus 1. Okay? And therefore, again you know k is equal to 2 pi over lambda. So this pi and this pi will now cancel out and the position of nth antinode denoted by this symbol xn is given by n times lambda by 2. Okay. Now after substituting these values of n, you can obtain the position of different antinodes. So let us put n equal to 0, then xn will be x0, which is 0. So one of the antinode is formed at the origin, at the place x equal to 0. Okay. Now n equal to 1, then x1 will be lambda by 2. This is the first antinode, this is the second antinode, and you can see the distance of the second antinode from the first antinode is equal to lambda by 2. And when n is 2, then this will be x2, and x2 will be 2 into lambda by 2, which is lambda. Okay. And similarly, the third antinode is located at 3 into lambda by 2. So now, again you can see, if you find the spacing between the first two antinodes, that will be x1 minus x0, that is lambda by 2 minus 0, which will be lambda by 2. The second and first antinode, x2 minus x1, that is 2 into lambda by 2 minus lambda by 2, that will be also equal to lambda by 2. So here you can also see that just like nodes, the antinodes are also equally spaced, and the spacing between two adjacent antinodes or two successive antinodes is again lambda by 2. Okay. And what is the maximum value of amplitude? This is plus minus 2a. Okay. Now, in fact, when you see here is antinode, here is antinode, and you have seen earlier that a node is lying here, okay, which is at a distance lambda by 4. Again here there is node. So actually the nodes and antinodes are formed alternately. Here is antinode, here is antinode, here is antinode, here is antinode, and between two antinodes there is a node. Okay. This is node. And the separation between an antinode and its adjacent node is lambda by 4. This distance will be lambda by 4. This distance will be lambda by 4. This distance will be lambda by 4. Okay. Actually, all these things I have shown in this figure. Here you can see in the graph I have shown it here. Okay. See this figure. In fact, you can see that at this x equal to 0, this is actually a graphical plot of sin against of x. Here x is 0, and this is the position of antinode, and here this is your maximum amplitude, which is plus 2a or minus 2a. And this is the position of the first node. This is second antinode. So in this way you can see in this figure the separation between two nodes n1 and n2 I have shown here. This is lambda by 2. The separation between this antinode A2 and the node n2 is lambda by 4. Okay. Sorry, this n2 and A3 I have shown lambda by 4. And again the separation between A3 and A4, that is third and fourth antinode, is lambda by 2. So all these things actually I have shown here. Actually, the region between two nodes is called a loop or segment. So you can say that actually these nodes divide the medium into loops or segments. Okay. In fact, you can see this figure. When you talk about the region between two nodes, that is called loop or segment. And here you must remember that all the particles in a segment or loop vibrate in same phase. Okay. You can see here this is at time t equal to 0, here there is a node, there is a node, and all the particles in this region will vibrate in same phase. Okay. But the phase of vibration at the same moment in an just adjacent loop will be just reverse. So you can say all the particles in a segment vibrate in same phase but in opposite phase with the particles in the adjacent segment. Okay. In fact, it is seen that twice in one period all the particles pass through their mean positions simultaneously with maximum velocity, and the direction of motion being reversed after each cycle. All these things I have actually shown here, and for your convenience I have written here. You can note down in your notebook. Okay. So this is a very remarkable fact. Okay. Now let us see the another important fact, which is a very important fact, and this will be discussed actually more rigorously in forthcoming video. I have mentioned here that this standing waves can be a transverse wave and it can be a longitudinal wave. It means a standing wave may be transverse and it may be longitudinal. For example, if you are talking about the waves on a string under tension, if reflected wave exists in this case, then it is of transverse nature. So on a stressed string, if reflected wave exists, then the standing wave is of transverse nature. But when you will study organ pipe, as you have studied already in case of vibration, then you will say that in organ pipe there is longitudinal stationary wave. Okay. So actually, in case of longitudinal wave, as pressure and displacement differ by pi by 2. I am actually mentioning this fact here without proof, but just after this video I will upload a video in which I will prove this fact, that if you are talking about sound wave, there may be two representation of sound wave, displacement representation and pressure representation. Although pressure representation is the best representation for sound wave, but in case of longitudinal wave, you may represent the wave by displacement of the particle in the medium, or you also may represent the wave in terms of the excess pressure of the medium. Okay? But the pressure representation differ in phase by pi by 2 with the displacement representation. It means if the displacement equation is in terms of sine function, then you will see that pressure representation will be in terms of cosine function. So phase will be just differ with pi by 2. And if phase will differ by pi by 2, what will happen? Just we have seen, in case of displacement wave, at nodal point displacement is minimum. But when you talk about this node formation in case of pressure wave, then you have to say that at the nodal points pressure is maximum. Okay? It means that the point where displacement will be minimum, pressure will be maximum. Okay? And similarly at antinodes, as you have seen, displacement is maximum. But if you are talking about the pressure wave, then this at the antinode pressure will be minimum. In fact, when I will prove this fact that the phase difference between the pressure and displacement wave is pi by 2, then this fact will be more clear to you. Okay? Now, in 7th point, I would like to explain why this wave is called a standing wave. As I have told you earlier, there is something which does not actually move, which does not transfer, which does not get transmitted, that remains static. Okay? Actually, what is that? That is energy. As you know, in case of traveling wave, energy flows continuously from one region to another. But what will happen when you talk about the standing wave? As you know, in case of a stationary wave, the nodes are permanently at rest. Okay? And since the nodes are permanently at rest, therefore, no energy can be transmitted across them. So, the energy of a loop remains confined to that very loop. Okay? And this is the reason of the name standing wave. But the energy of a loop is although confined to the loop, but there is a variation or there is a oscillation of the energy from potential energy to kinetic energy and kinetic energy to potential energy. Just as you have learnt in case of the simple harmonic motion, that when your particle passes from the equilibrium position, at equilibrium position, you know, potential energy is zero and kinetic energy is maximum, which is equal to the total energy. But as the particle reaches to the extreme position, potential energy becomes maximum and kinetic energy becomes zero. Okay? So in this way, there is a change of potential energy, kinetic energy to potential energy as the particle moves from equilibrium position to the extreme position. And similarly, when the particle moves from extreme position to equilibrium position, then potential energy converts into kinetic energy. And at the equilibrium position, 100% energy is in the form of kinetic energy. But always the sum of these two energy remains constant. That is the potential energy plus kinetic energy that remains conserved. Okay? So in a particular loop, there is a transformation of energy from kinetic to potential and potential to kinetic, but the total energy of a loop remains conserved. It does not flow from one loop to another. If let us say these are two loops, the energy of this first loop is confined to it, energy of the second loop is confined to it, and this is the reason of the name standing wave or stationary wave. Due to this characteristic, this wave is called a standing wave or a stationary wave. Now finally, this is our last point of discussion, in which we are going to see a very important parameter which is called a standing wave ratio, denoted by the symbol SWR, which is actually a measure, which will be just a number, and that actually measures what is the degree of the property of a standing wave. In fact, as I have told you during the definition in the beginning of my lecture, that when two waves of equal amplitude, equal frequency, moving in opposite direction with equal speed get superposed, a standing wave is formed. This is an ideal definition. It is not necessary that the superposing wave will have always equal amplitude. The amplitude may be different. But even then, when the amplitude of two waves will be not equal, even then, due to superposition, a standing wave will be formed. But that will be not a perfect standing wave. How much its perfectness is lost, that is measured in terms of a quantity which is called a standing wave ratio. Okay? So, if you consider that now in case of formation of a standing wave, the two waves which actually take part are of unequal amplitude, not of equal amplitude. If their amplitudes are unequal, then minimum amplitude of the standing wave will be not zero, and therefore if you find the displacement at nodal points, psi n means displacement at node, then that will be equal to as minimum times sine omega t. It means displacement at nodes will be minimum but not zero. But when the amplitude of both waves are superposing waves are or component waves are equal, then since this as minimum is zero, that's why psi is zero. Okay, so in this case at the nodal points actually the amplitude is not zero, so displacement will be not zero, and therefore the particles at the nodes will be not permanently at rest. And if the particles at the nodes are not permanently at rest, there will be a transfer of energy from one loop to another in this case. Okay? And so you can say that in a strict sense, this wave is not a pure standing wave. In this condition, we simply say that wave is partially stationary, not pure stationary. Okay? So I have mentioned it here. It means nodes will be not permanently at rest, and so some energy will pass across the node and the wave will be partially standing. Have you understand? Now, how much this, what is the degree of the stationary wave in this wave? That is measured actually in terms of a parameter or which is called a standing wave ratio. So I have mentioned here, in such situations we estimate the extent to which the resultant wave is standing by a parameter, a standing wave ratio, SWR. And how this SWR is defined? It is defined as AS maximum divided by AS minimum. So you can see this is just a number because it is a ratio of two amplitudes, maximum amplitude divided by minimum amplitude. Now if you consider that A1 and A2 are the amplitudes of the waves which get superposed to form the standing wave, then AS maximum will be A1 plus A2 and AS minimum will be A1 difference A2. I have written difference, not A1 minus A2. Among A1 and A2, which will be larger, we will subtract from that another amplitude. So so we have taken different sign here. So when now you can see, if we are not talking about a progressive wave, then what will be this SWR? If you are talking about progressive wave, there is no superposition. There will be only one wave. So in this condition, we will have A2 barabar 0 because there is only one wave. Second wave is not present. And if A2 is 0, you can see here, then that this SWR will be equal to what? This will be A1 divided by A1 and that is equal to 1. Actually, this is the minimum value of SWR. A standing wave ratio has least value equal to 1. It means progressive wave has no property of a standing wave. No property of a standing wave. Okay. Now consider the case of perfectly standing wave as you have discussed the theory. You have seen that if you are talking about a perfect standing wave, that will be created, that will be produced only when the amplitude of both of the superposing components are equal. That is A1 is equal to A2. Then what will be SWR? This will be 2A divided by 0 because in this condition A1 plus A2 will be equal to 2A because A1 and A2 both are A, and A1 difference A2, this will be equal to 0. So this will be undefined, infinity. So SWR for a perfect standing wave is infinite. This is actually the maximum value of SWR. So you can say that actually the value of SWR for all other wave, if you are talking about a stationary wave, the SWR is minimum at a value 1. If you are talking about the perfect standing wave, its value is infinity. So basically you can say that for all other waves, the value of this SWR will lie between 1 and infinity, greater than 1 and less than infinity. Okay. So in this way, you can see this SWR is a very important parameter to decide that how much the property of a standing wave is found in a wave. Okay. So I think after these 8 points of discussion, the each and every aspect or regarding this standing wave is now clear to you. Okay. Thank you very much.